In the universe, planets are as widespread as stars, and although they can radically differ from one another, they all share common characteristics, key features that can give us an idea of how they formed. And knowledge of the life cycles of stars and their planetary systems gives us an understanding of the mechanisms that gave rise to them. By studying this, we begin to understand the processes through which our own solar system was born. Today, the solar system is a little over 4.5 billion years old, and it is home to 8 planets, 4 small rocky ones, 2 gas giants, and 2 large icy planets. 6 of these planets have at least one moon, and the largest ones, Jupiter and Saturn, have dozens of moons. Some of these moons are so large that they could be independent worlds if they didn't orbit a giant planet. In addition to all these moons and planets, our solar system contains dozens of dwarf planets, millions of rocky asteroids, and trillions of icy bodies arranged in belts within the solar system. The outer part of the solar system consists of the Kuiper belt and the more distant hypothetical Oort cloud. Today, in the solar system, there is equilibrium, and each of its 8 planets orbits predictably. Small rocky planets are located closer to the Sun, while the larger ones are much farther away. For a long time, astronomers believed that planets are arranged this way in all planetary systems. However, starting in 1995, we gained the ability to observe the surroundings of planets in other star systems. It turned out that not all planetary systems are neatly structured, and they are not evenly populated. Planets of all sizes and types can be scattered throughout systems, and they do not necessarily follow circular orbits. In fact, the dynamism of planetary systems is a fundamental property that can radically change the fate of a planetary system, and it seems that we are an exception. But despite the clear arrangement of planets, it is entirely possible that the solar system once looked very different. Unfortunately, humanity appeared on the scene quite late to witness the young solar system firsthand. But we can see the consequences of key events that occurred early in its life. Thanks to space telescopes like Hubble and Kepler, we have explored, cataloged, and characterized thousands of other systems at every stage of their evolution, from birth to death. The birth of stars begins inside massive cold gas and dust clouds or nebulae. These contain a variety of different chemical elements and compounds, primarily hydrogen and helium, but also, in smaller proportions, more complex elements. For example, organic hydrocarbon molecules and various forms of volatile substances like water and methane. These clouds are so vast that stars form within them not in isolation but as star clusters. Approximately 90% of stars, including our Sun, are born in what could be described as nurseries or clusters. These star clusters gradually disperse under the influence of gravity. What makes nebulae conducive to star formation is their gravitational instability, strong asymmetry with uneven mass distribution, and constant motion. Consequently, these gas and dust clouds tend to internally fragment with areas of higher density, causing them to collapse under the force of gravity, forming denser gas pockets. It is within these pockets, also known as protostellar nebula, that star systems like the solar system are formed. The birth of such a system always begins with angular momentum. While all the necessary ingredients for a star are present in a protostellar nebula, something must trigger the collapse of the cloud to form a star. Once gravity begins to act on the gas and dust pocket, it starts to rotate, creating a vortex and drawing all its contents inward. This process takes millennia, until an accretion disk is formed. The rotation of this disk accelerates as it approaches the core, where matter compresses and heats up increasingly. This process continues for about 100,000 years until the heated gas and dust condense in the central region, forming the core of the disk from which a star will eventually be born. As gas continues to flow into the central region, it accumulates and swirls around the core, heating up and acting like a gas furnace, increasing density and temperature. Eventually, there is enough mass and pressure for the star to ignite. And this is just the beginning, the first stage of a star's birth. At this point, the star is not yet hot enough and not massive enough to initiate nuclear fusion, the process that transforms a nascent star into a main sequence star, like our Sun. For example, when a star becomes at least 13 times more massive than Jupiter, it is at this point that it reaches the stage where nuclear fusion can begin. However, regardless of its overall mass, it is incapable of fusing hydrogen and instead fuses deuterium, which produces much lower outward pressure. If the mass accumulated by the star during its incubation does not exceed roughly 80 times Jupiter's mass, then in this case, the star will not progress further. Deuterium burning will be insufficient, and the star will remain a brown dwarf. However, stars whose mass exceeds this limit can synthesize hydrogen and gradually, over about 1 million years, transform into a main sequence star. At this time, the accretion disk becomes a protoplanetary disk, and at this stage, there is a brief window of opportunity for planet formation. This is a crucial moment for a planetary system because while planets may take billions of years to change and evolve, they must form within a relatively short astronomical window of 10 million years, or they may never form at all. In the dense environment of the spinning protoplanetary disk, dust particles attract and stick to each other, growing at a rate of a few centimeters per year. It takes about 1 million years for these dust particles to form planetesimal embryos about 1 kilometer in size. Once planetesimals form, they start attracting more and more material from the protoplanetary disk, forming larger bodies. As a result, over the course of 1 million years, the processes of accretion lead to the formation of rocky planets over 1,000 kilometers in diameter. These bodies dominate their regions in the disk, attracting an increasing portion of the remaining material consisting of smaller objects. After planetesimals formed in part of the protoplanetary disk and the other part was dispersed, these planetary embryos start colliding with each other, merging into rocky bodies reaching a certain size, becoming massive enough for their heavier elements and metals to sink towards the heated core. These planetary embryos gradually evolve into planets with a heated, multi-layered interior structure. This is how rocky planets like Mercury, Venus, Earth, and Mars are formed. Typically, they are found closer to their parent star. However, silicates make up only a portion of the mass of the protostellar nebula, so there isn't enough silicate material for terrestrial group planets to become larger. Most of the protoplanetary nebula consists of hydrogen and helium, which remains in the disk as planets begin to form. Beyond the orbit of Mars, there isn't enough heat generated by the star. Space here becomes cold enough for volatile substances ejected from the hot disk to condense into a solid form known as ice. These newly formed icy blocks become the planets located farther from the star. Planetary embryos that attract these ices can quickly grow to be many times the mass of some terrestrial group planets. They become heavy enough to begin attracting hydrogen and helium from the surrounding disk before being ejected further by the young star. These hydrogen and helium atoms form a dense atmosphere around the icy core of the planet, ultimately becoming so large and massive that they become extremely compressed spheres of liquefied gases, known as gas giants. These are Jupiter and Saturn. Ice giants, such as Uranus and Neptune, are considered failed gas giants that formed later. However, according to astronomers, they still retain thick envelopes of volatile substances and are many times more massive than Earth. Whether they are gas or ice giants, these massive planets orbit their orbits, crossing orbital lines, creating gravitational impacts that can disrupt the orbits of other planets. Planetary material that remained unused after the formation of rocky planets was scattered by these gravitational pushes, partly accumulating into small, near-star belts consisting of rock and ice. This is how, roughly after 10 million years, the formation of planets comes to an end. It took the Sun approximately 50 million years to fully transform into a yellow dwarf on the main sequence, synthesizing hydrogen, and another 50 million years for the terrestrial group planets to fully form as we know them today. After the formation of Jupiter and Saturn, their gravitational influence pushed Neptune and Uranus to their current orbits. Neptune's intrusion into its current orbit disrupted the tranquility in this region, causing some debris to be sent to the more distant regions of the solar system, where they now comprise the Kuiper belt, while some were sent into the inner part of the solar system, subjecting Earth to asteroid impacts for about 300 million years. The orbits of icy planetesimals were also disrupted by the gravity of the gas giants. They, like asteroids, returned to the inner part of the solar system as comets, which also collided with Earth and other terrestrial group planets. Water contained in these comets vaporized upon impact, but this vapor was retained by the early planet's atmosphere. When the planets cooled down sufficiently, the atmospheric balance changed, allowing the vapor to condense and fall as rain, which poured continuously for thousands of years, filling basins and eventually creating entire oceans of liquid water. Currently, we know that Earth has liquid water, but astrophysicists claim that in the early solar system, it is highly likely that 3 planets, Venus, Earth, and Mars, were covered with water. However, due to cosmic and geological processes spanning over 2 billion years on Mars, the water froze, while on Venus, it evaporated. Only Earth retained water in liquid form. It is believed that multicellular life on Earth took about 3 billion years to evolve and give rise to humans. 2 of our neighboring planets were once similar to Earth. However, today, neither of them can boast anything remotely close to the intricate set of idealistic properties that make our planet unique. Today, Earth's natural balance is sustained by the life processes it has generated, remaining at an optimal distance from the Sun to maintain a moderate climate for millions of years. Earth is a success story, an exceptional world, a thriving oasis warmed by the rays of a star called the Sun. As long as the sun shines, take care of yourselves and your loved ones. Until the next, even more fascinating cosmic encounters.